Picture this. The universe wasn't always filled with stars, galaxies, and cosmic wonders. There was a time just after the explosive birth of everything, when space itself glowed like the embers of a fading fire. That ghostly afterglow, it's still all around you right now, a cosmic whisper from 13.8 billion years ago. This is the cosmic microwave background, the oldest light in existence, and it holds secrets that will completely change how you see reality. From accidental discoveries that won Nobel Prizes to bizarre anomalies scientists still can't explain, the CMB is like a treasure map to the universe's past and future. Why does it look the same in every direction? Could its patterns hint at other dimensions, or even other universes? And how does something this ancient still shape the cosmos today? Stick around, because we're about to blast through 25 mind-blowing facts about this celestial time capsule. By the end, you'll never look at static on an old TV the same way again. Trust me, you're in for some cosmic-level surprises. Here's how the next section would flow seamlessly from your introduction while maintaining engagement and clarity. Now, let's peel back the first layer of this cosmic mystery. Imagine stepping outside on a clear night, turning in every direction and seeing the same faint glow. No matter where you look, that's exactly what the cosmic microwave background is doing right now, bathing the entire universe in its ancient light. It's not just somewhere out there, it's everywhere, a literal fossil of the Big Bang's aftermath. This all-pervasive radiation comes from a pivotal moment in cosmic history, just 380,000 years after the universe began. Before that, space was a searing, opaque fog of charged particles, so dense that light couldn't travel freely. But as the cosmos expanded and cooled, atoms finally formed, releasing a flash of light, the CMB's first photons. Stretched by billions of years of cosmic expansion, that light now reaches us as microwaves, barely warmer than absolute zero at 2.7 Kelvin. But here's the puzzle that baffles scientists. Why is this glow so eerily uniform? No matter which patch of sky we observe, the temperature varies by less than 100,000th of a degree. That's like heating a cup of coffee in Tokyo and finding it's identical to one in New York, down to the tiniest fraction. Such uniformity defies expectations because in the universe's chaotic infancy, there wasn't enough time for heat to spread evenly across cosmic distances. This horizon problem led theorists to propose a jaw-dropping solution: cosmic inflation, a split-second period where the universe expanded faster than light itself, smoothing out wrinkles like a balloon inflating. Yet even this raises new questions. Why this temperature? Why this pattern? The CMB's uniformity isn't just a relic, it's a cosmic detective story, and we're just starting to piece together the clues. What's wild is that you've experienced the CMB without realizing it. Ever seen static on an old TV? About 1% of that snow comes from photons left over from the Big Bang. So next time you glance at the night sky, remember, you're not just looking at stars, you're swimming in an ocean of ancient light, and its whispers hold the universe's deepest secrets. Now, here's something that might surprise you. The discovery of the cosmic microwave background wasn't the result of some grand, deliberate quest. It was pure serendipity, a cosmic accident that changed our understanding of the universe forever. Back in 1965, two radio astronomers, Arno Penzias and Robert Wilson, were working at Bell Labs in New Jersey, trying to calibrate a massive horn-shaped antenna. Their goal was simple: eliminate all interference to improve satellite communications. But no matter what they did, there was this faint, persistent noise, a hiss that wouldn't go away. They checked everything. They scrubbed the antenna clean of pigeon droppings, ruled out equipment malfunctions, even considered nearby radio signals. Nothing explained the static. Then they stumbled upon a groundbreaking idea. What if this noise wasn't interference at all? What if it was coming from space itself? Around the same time, a team of astrophysicists at Princeton, led by Robert Dicke, had predicted the existence of leftover radiation from the Big Bang. When Penzias and Wilson heard about this, the pieces clicked. That annoying hiss, it wasn't a flaw in their equipment. It was the faint echo of the universe's birth, radiation that had been traveling for 13.8 billion years to reach us. The implications were staggering. This discovery silenced skeptics of the Big Bang theory because here was tangible proof that the universe had a fiery, explosive beginning. Before this, the steady-state theory, which claimed the universe had no start or end, was a popular alternative, but the CMB's existence shattered that idea, cementing the Big Bang as the cornerstone of modern cosmology. And here's the kicker: Penzias and Wilson weren't even looking for it. They were just two engineers trying to fix a radio, yet their accidental breakthrough earned them the Nobel Prize in Physics in 1978, proving that sometimes the biggest discoveries come when you least expect them. What makes this even more fascinating is how humble those first observations were. The CMB's signal was incredibly faint, just a whisper above absolute zero. But in that whisper lay the blueprint of the cosmos, the oldest light in existence. It's a reminder that science isn't just about grand experiments, it's about curiosity, persistence, and recognizing the extraordinary in the seemingly mundane. So the next time something doesn't go according to plan, remember Penzias and Wilson. That frustrating glitch, that unexplained noise, it might just be the universe trying to tell you something incredible. Now, let's turn the page to one of the most pivotal moments in cosmology: how the cosmic microwave background didn't just hint at the Big Bang, it proved it. Before the CMB's discovery, the universe's origin was a battleground of ideas. The steady-state theory, championed by brilliant minds like Fred Hoyle, argued that the universe had no beginning or end. It simply was, eternally expanding while new matter quietly appeared to fill the gaps. It was elegant, philosophical, and for a time, a serious rival to the Big Bang. But the CMB changed everything. That faint static Penzias and Wilson stumbled upon wasn't just noise, it was the smoking gun. Think of it like finding a fossilized footprint. Just as a footprint proves something walked there, the CMB's uniform glow proved the universe was once unimaginably hot and dense. Here's why. The Big Bang theory predicted that in its fiery infancy, the universe was a plasma so dense that light couldn't travel freely. After about 380,000 years, it finally cooled enough for atoms to form, releasing a burst of light, the very first photons. Over billions of years, that light stretched into microwaves, becoming the CMB we detect today. The steady-state theory, on the other hand, had no explanation for this radiation. If the universe had no beginning, there'd be no reason for this blanket of microwaves to exist. The CMB's discovery didn't just support the Big Bang, it obliterated the competition. Even Fred Hoyle, the steady-state's most vocal defender, eventually conceded. But the CMB's confirmation didn't stop there. It also answered a haunting question: why is the universe so uniform? When we look at the CMB, its temperature is nearly identical in every direction, down to a fraction of a degree. That uniformity would have been impossible unless the universe started as a single, ultra-hot point that expanded rapidly, smoothing out variations. This became the foundation for cosmic inflation theory, the idea that the universe underwent a faster-than-light growth spurt in its first split second. And here's where it gets even more fascinating. The CMB's tiny fluctuations, those millionth of a degree variations, aren't imperfections, they're cosmic blueprints. Without them, gravity wouldn't have had anything to work with, and galaxies, stars, and planets might never have formed. So when you look up at the night sky, you're seeing the amplified result of those microscopic wrinkles in the CMB. What's remarkable is how simple the proof was. No grand equations, no billion-dollar experiments, just two engineers with a radio antenna and an open mind. The CMB didn't just confirm the Big Bang, it showed us that the universe has a story, one written in light and decoded by curiosity, and that story, it's still being told. Now let's zoom in on something extraordinary, those barely there imperfections in the cosmic microwave background. At first glance, the CMB looks like a smooth, uniform glow, but if you peer closer, you'll find it's peppered with tiny temperature variations, fluctuations so slight they're just millionths of a degree apart. These minuscule ripples might seem insignificant, but they're the universe's way of leaving breadcrumbs for us to follow. Imagine blowing up a balloon with tiny dots scattered across its surface. As the balloon expands, those dots stretch apart, but their pattern remains. That's exactly what happened with the CMB's fluctuations. They're frozen echoes of the universe's earliest moments, stretched and diluted over billions of years. These anisotropies, as scientists call them, are cosmic fingerprints revealing the seeds of everything we see today. Without them, the universe would be a featureless void, no galaxies, no stars, no planets. The story of how we mapped these wrinkles is just as fascinating. Before the 1990s, scientists suspected these fluctuations existed, but they were too faint to detect with the technology of the time. Then came NASA Cosmic Background Explorer, or COBE, a satellite designed to listen to the universe's oldest whispers. In 1992, the COBE team unveiled the first detailed map of the CMB, and it was revolutionary. The data showed a patchwork of hot and cold spots, variations so delicate they were like detecting the difference between a calm pond and one with ripples the width of a human hair. What's mind-bending is what these fluctuations tell us. They're the aftermath of quantum mechanics playing out on a cosmic scale. In the universe's first moments, subatomic particles jostled and danced, creating tiny density differences, some regions slightly more packed, others a bit more sparse. Over time, gravity amplified these differences, pulling matter into the denser regions, sculpting the cosmic web of galaxies we see today. The CMB's fluctuations are, in effect, the universe's original blueprints, a snapshot of its potential before anything had fully formed. But here's the kicker: the size and distribution of these fluctuations are eerily precise. They match predictions made by cosmic inflation theory, the idea that the universe underwent a rapid expansion in its first fraction of a second. The patterns we see are too uniform to have formed by chance, suggesting that inflation smoothed out the universe while leaving behind these quantum imprints. It's like finding a perfectly preserved fossil that confirms not just how life evolved, but how it began. And the discoveries didn't stop with COBE. Later missions, like the Wilkinson Microwave Anisotropy Probe and the Planck satellite, sharpened the image, revealing even finer details. These missions showed that the fluctuations aren't random, they follow a mathematical rhythm, a cosmic symphony composed in the universe's first moments. So the next time you gaze up at the night sky, remember, the stars and galaxies aren't just scattered randomly. They're the grown-up versions of those tiny wrinkles in the CMB, the result of quantum quirks magnified by time and gravity. What began as whispers in the static became the grand story of the cosmos, and we're just beginning to read it. Now, let's step back and marvel at what the cosmic microwave background truly represents: a baby picture of the universe frozen in time. Think of it like this: if the universe's lifespan were a feature-length film, the CMB captures a single frame from the opening seconds. It's a snapshot of the cosmos when it was just 380,000 years old, a mere 0.003% of its current age. At that moment, the universe transitioned from a seething, opaque soup of particles to a transparent expanse where light could finally travel freely. And that first light, that's the CMB we detect today. Before this cosmic milestone, the universe was too hot and dense for atoms to form. Electrons and protons raced around, scattering photons in a chaotic dance, making space as murky as a foggy morning. But as the universe expanded and cooled, something extraordinary happened. electrons and protons combine to create neutral hydrogen atoms. Suddenly, photons, those particles of light, could zip through space without constantly bumping into charged particles. This moment, called recombination, marked the universe's first clear breath, and the CMB is the afterglow of that instant. It's like the universe's first baby photo, taken the moment it opened its eyes. What makes this snapshot so precious is its purity. The CMB isn't just old light, it's undisturbed light. For billions of years, it's traveled across the cosmos, barely altered by the galaxies and voids it passed through. That's why it's such a powerful time capsule. When we study its patterns, we're not just seeing the universe as it was, we're seeing it before stars or galaxies even existed. It's a blank canvas with the faintest pencil sketches of structures to come. To put this in perspective, imagine you're holding a photograph of your grandparents as toddlers. You'd see hints of the people they'd become, their expressions, their posture, but none of the wrinkles, scars, or wisdom of their later years. The CMB is like that, but for the cosmos. Its tiny fluctuations are the genetic code for everything that followed: the galaxies, the superclusters, the vast cosmic web. But in this snapshot, they're just whispers, subtle variations in temperature that would take billions of years to grow into the universe we recognize. And just like a baby photo, the CMB holds clues we're still decoding. The exact distribution of those temperature fluctuations tells us about the universe's composition, its rate of expansion, even its shape. It's as if the universe left us a meticulously labeled baby book, and we're still turning the pages. Every new observation from satellites like Planck adds another layer of detail, helping us understand not just how the universe grew up, but how it was born. So when you hear scientists call the CMB a baby picture, they're not being poetic, they're being precise. It's the earliest, clearest glimpse we have of our cosmic origins, a window into a time before time as we know it. And just like any family album, it's a reminder of how far we've come and how much more there is to discover. Now, here's something that might blow your mind. The cosmic microwave background isn't just a pretty picture. It's a cosmic ledger, a detailed breakdown of what the universe is actually made of. Those tiny temperature fluctuations we've been talking about, they're not random. They're like fingerprints revealing the exact recipe of our cosmos, and what they tell us is downright astonishing. The universe we see, the stars, planets, even you and me, makes up just a tiny fraction of everything that's out there. Let's break it down. The CMB's patterns show that ordinary matter, the stuff you're familiar with like atoms, molecules, and all the things that glow in the night sky, accounts for a mere 5% of the universe's total content. That's right, everything we can see, touch, or study in labs is just a drop in the cosmic bucket. The rest, well, that's where things get wild. 27% of the universe is something called dark matter, an invisible, mysterious substance that doesn't emit light or interact with electromagnetic forces, but whose gravity holds galaxies together like cosmic glue. And the remaining 68%, that's dark energy, an even more baffling force that's causing the universe to expand at an accelerating rate. So how does the CMB reveal all this? Think of it like reading ripples on a pond. The way those temperature variations are distributed across the sky tells scientists how much matter, both ordinary and dark, exists in the universe. The patterns match predictions made by supercomputer simulations, but only if you include dark matter's gravitational pull. Without it, galaxies wouldn't spin the way they do, and the large-scale structure of the cosmos wouldn't make sense. The CMB's data is what finally convinced skeptics that dark matter isn't just a mathematical fudge, it's real, and it's everywhere. Then there's dark energy. This one's even stranger. Back in the 1990s, astronomers studying distant supernova made a shocking discovery. The universe's expansion isn't slowing down as everyone expected. It's speeding up, but to explain that, you need something pushing space itself apart, something invisible, pervasive, and relentless. Enter dark energy. The CMB's measurements of the universe's geometry and expansion rate align perfectly with this eerie conclusion. In fact, the CMB's data is so precise that it pins dark energy's contribution at that jaw-dropping 68%. What's especially mind-bending is how the CMB solved one of cosmology's biggest headaches, the missing mass problem. For decades, astronomers noticed that galaxies were moving in ways that didn't add up. There simply wasn't enough visible matter to account for their motions. Some even joked that the universe was playing hide and seek with its own ingredients. But the CMB's map revealed the hidden players, dark matter's gravity and dark energy's push. Suddenly, the math worked, the universe's ledger balanced. Here's why this matters. Without the CMB, we'd still be staring at the night sky, wondering where 95% of the universe went. It's like trying to understand a movie by only watching 5% of the frames. The CMB filled in the missing reels, showing us that the cosmos is far weirder and far more fascinating than we ever imagined. And the crazy part, we're still just scratching the surface. Every new study of the CMB peels back another layer, revealing deeper mysteries about the dark universe we're only beginning to explore. So next time you hear about dark matter or dark energy, remember, it's the cosmic microwave background that handed us the cosmic cheat sheet. And if that doesn't make you look at the night sky a little differently, well, maybe nothing will. Now let's take a step back and look at the big picture, literally. The cosmic microwave background doesn't just tell us what the universe is made of. It also answers one of the oldest questions in cosmology: what shape is the universe? And the answer, according to the CMB, is surprisingly simple. It's flat. Not flat like a sheet of paper, but flat in the geometric sense. A universe where parallel lines stay parallel forever, and the angles of a triangle always add up to 180 degrees. How does the CMB prove this? It all comes down to those tiny temperature fluctuations we've been talking about. Their size and distribution across the sky act like a cosmic ruler, measuring the geometry of the universe itself. Here's how it works. Imagine you're looking at a pattern of ripples on the surface of a pond. If the pond were curved, like a bowl or a saddle, the ripples would appear distorted, stretched or squeezed depending on the curvature. But if the pond is flat, the ripples keep their original shape. The CMB's fluctuations are those ripples, and their near-perfect preservation tells us the universe has no overall curvature. To put it another way, think of space as a giant balloon being inflated. If the universe were positively curved like the surface of a sphere, the balloon would eventually wrap back on itself. Parallel lines would meet, and triangles would have angles adding up to more than 180 degrees. A negatively curved universe shaped like a saddle would do the opposite. Parallel lines would diverge, and triangles would have angles totaling less than 180 degrees. But the CMB's data shows neither. Instead, the fluctuations match exactly what you'd expect if the universe were perfectly flat. Just like a balloon stretched so large that any tiny patch of it feels flat to the touch. This flatness is a smoking gun for cosmic inflation, the theory that the universe underwent an unimaginably rapid expansion in the first fraction of a second after the Big Bang. Inflation would have stretched space so much that any initial curvature was smoothed out, leaving behind the flat geometry we see today. It's like blowing up a balloon to the size of a planet. No matter how wrinkled or curved it started at that scale, every little patch would appear flat. The CMB's confirmation of flatness is one of the strongest pieces of evidence we have that inflation really happened. But here's where it gets even more interesting. A flat universe has profound implications for its ultimate fate. In a positively curved universe, gravity would eventually win, pulling everything back together in a big crunch. A negatively curved universe would expand forever, thinning out into cold emptiness. But a flat universe, it's right on the knife's edge. Without dark energy, it would expand forever, but at a slowing rate. Throw dark energy into the mix though, and the expansion accelerates, leading to the scenario we see today, where galaxies are being pushed apart faster and faster. The CMB's flatness isn't just a neat fact, it's a cornerstone of modern cosmology. Without it, we'd be stuck in a debate about the universe's shape that dates back to Einstein. Instead, we have a clear answer, one that ties together inflation, dark energy, and the very structure of reality. And the next time you look up at the night sky, remember, you're not just seeing stars. You're gazing out into a universe so vast and perfectly balanced that its flatness is written into the oldest light there is. Now, let's peel back another layer of this cosmic onion. The cosmic microwave background isn't just about temperature, it's also polarized, and that polarization holds secrets about the universe's wild infancy. Picture sunlight reflecting off a lake. The light waves scatter in a particular direction, creating a glare. That's polarization in action, and the CMB has its own version, imprinted when its light last interacted with matter over 13 billion years ago. But here's where it gets fascinating. The CMB's polarization comes in two distinct flavors, E modes and B modes. Think of E modes as the universe's fingerprint patterns created by the density variations in the early cosmos, the same wrinkles that seeded galaxies. They're like the gentle ripples you'd see if you tapped the surface of that lake. B modes, though, are the real showstoppers. These twisting, swirling patterns are the smoking gun of primordial gravitational waves, ripples in spacetime itself, stirred up during the universe's explosive growth spurt in the first fraction of a second after the Big Bang. Detecting B modes is like finding the echo of a cosmic shout. Gravitational waves from inflation would have stretched and squeezed spacetime, leaving behind a telltale swirl in the CMB's polarization. It's the kind of discovery that could clinch the case for cosmic inflation, the theory that the universe ballooned from smaller than an atom to macroscopic size in less than a blink. Experiments like BICEP, stationed at the South Pole to avoid atmospheric interference, have hunted these elusive B modes for years. In 2014, they made headlines with a tantalizing signal, but it turned out to be dust in our own galaxy mudding the data. That's where the Planck satellite stepped in. While Planck's primary mission was mapping the CMB's temperature, it also delivered the most detailed polarization map yet, helping separate the cosmic signal from local noise. Together, these missions have painted a clearer picture. B modes are there, but they're fainter than we'd hoped, buried under the chatter of galactic dust and other foregrounds. The hunt isn't over, though. Next-generation telescopes with even sharper vision are gearing up to tease out these whispers from the dawn of time. Why does this all matter? Because B modes aren't just a curiosity. They're a direct line to energy scales 1 trillion times higher than what our particle accelerators can reach. If we can confirm their inflationary origin, it's like getting a postcard from the universe's first moment, written in the language of gravity, and that's the magic of the CMB's polarization. It's not just light, it's a time capsule, a forensic record, and maybe, just maybe, the key to understanding how everything began. Here's the next section of the script, flowing naturally from the previous discussion on polarization. Now, let's shift gears and talk about something equally mind-bending. The cosmic microwave background isn't just fading into the background, it's literally cooling down as the universe ages. Think of it like a cup of coffee left on the counter. Over time, it loses heat, but instead of minutes, this cosmic brew has been cooling for over 13 billion years. When the CMB first burst onto the scene, it wasn't the faint microwave whisper we detect today. Back then, just 380,000 years after the Big Bang, it was a blazing glow, hotter than the surface of some stars, clocking in at around 3,000 Kelvin. That's scorching enough to ionize atoms, turning the universe into a seething plasma soup. But as space expanded, stretching the fabric of the cosmos, those light waves stretched too. Longer wavelengths mean lower energy and lower temperature. It's the same physics that makes a fire truck's siren sound deeper as it speeds away, but on a universe-sized scale. Today, the CMB sits at a frosty 2.7 Kelvin, barely above absolute zero. Yet here's the kicker, it's still cooling. As the universe keeps expanding, that temperature will keep inching downward, asymptotically approaching absolute zero but never quite getting there. Even 1 trillion years from now, future cosmologists, if any exist, might still catch whispers of this ancient light, though it'll be so redshifted it'll barely register. This cooling isn't just a cosmic curiosity. It's a direct consequence of the universe's expansion, a living record of how space itself has stretched over time. The CMB's temperature is like a cosmic thermometer ticking down with each passing eon. And while it might seem like a slow process, remember, this drop from 3000 Kelvin to 2.7 Kelvin encapsulates the entire history of the cosmos, from the formation of the first atoms to the rise of galaxies, stars, and us. What's wild is that this cooling isn't uniform everywhere. Remember those tiny fluctuations we talked about earlier? They mean some patches of the CMB were ever so slightly hotter or cooler from the start, and that variation has been preserved like fossils in the cosmic record. Even as the whole thing chills out, those fingerprints of the early universe remain, telling us where matter was denser and where gravity would later sculpt galaxies. So next time someone says space is cold, you can nod knowingly. It's not just cold, it's getting colder, and the CMB is our ultimate proof. And somewhere in the far, far future, that afterglow will still be there, a ghostly echo of the universe's fiery birth, fading but never quite disappearing. Now let's venture into one of the most tantalizing possibilities the cosmic microwave background offers. What if it's hiding evidence of other universes? This isn't science fiction. Some scientists believe anomalies in the CMB, like the infamous cold spot, could be cosmic bruises left by a collision with another universe in the multiverse. Picture this, a mysterious region in the sky where the CMB is significantly cooler than surrounding areas, as if something drained its energy. But here's the twist. The cold spot isn't just a little chilly. It's a colossal void spanning nearly 1 billion light-years, with temperatures dipping far below what standard cosmology predicts. So how could this hint at a multiverse? One wild theory suggests that if our universe is just one bubble in a vast multiverse foam, these bubbles might occasionally bump into each other. A collision with another universe could leave an imprint like a fingerprint on glass, distorting the CMB in ways that defy conventional explanations. The cold spot's unusual properties, like its strange polarization patterns and lack of surrounding galaxies, make it a prime candidate for such an exotic origin. But before you start imagining cosmic border wars, let's be clear. This idea is highly controversial. Most mainstream cosmologists argue the cold spot could just be a statistical fluke, a rare but natural fluctuation in the CMB's otherwise smooth tapestry. Others propose less flashy explanations, like it being a supervoid, a vast, empty region of space where matter is unusually sparse, causing light passing through to lose energy and appear cooler. Yet the multiverse hypothesis refuses to fade. Why? Because the CMB is riddled with other oddities that don't quite fit the standard model. For instance, there's the so-called axis of evil, a perplexing alignment of CMB fluctuations along a preferred direction, almost as if the universe has a hidden tilt. Then there's the hemispherical asymmetry, where one half of the sky shows slightly different temperature patterns than the other. These anomalies are like cosmic breadcrumbs, leading some researchers to wonder if they're glimpses of physics beyond our universe. The stakes here are enormous. If even one of these irregularities turns out to be evidence of a multiverse, it would revolutionize our understanding of reality. Imagine confirming that our universe is just one page in an infinite cosmic library, each with its own laws of physics. And this is a big but extraordinary claims require extraordinary evidence. Right now, the cold spot and its siblings remain unexplained, not undeniable proof. future telescopes like the European Space Agency's proposed CMB mission Light Bird could settle the debate by mapping the CMB with unprecedented precision, hunting for more clues. For now, the cold spot is a cosmic riddle wrapped in a mystery. Whether it's a multiverse collision, a supervoid, or just a statistical oddity, it reminds us that the CMB isn't just a relic, it's a detective story, with each anomaly a potential clue to the universe's deepest secrets. And if the multiverse is real, our cosmic backyard just got a lot bigger. Now, shifting our gaze to another cosmic puzzle, let's talk about how the cosmic microwave background is at the heart of one of modern astronomy's most heated debates, the Hubble tension. This isn't just a minor discrepancy, it's a full-blown clash between two ways of measuring how fast the universe is expanding, and the CMB sits right in the middle of it. Here's the problem. When scientists use the CMB to calculate the Hubble constant, the rate at which the universe is expanding, they get one number. But when they measure the same thing using nearby stars and galaxies, they get a different number. And these numbers aren't just slightly off, they disagree by enough to keep cosmologists awake at night. The CMB method, based on the pristine light from the early universe, suggests an expansion rate of about 67 kilometers per second per megaparsec. Meanwhile, local measurements like those from supernova or pulsating stars peg it closer to 73. That gap might sound small, but in the precise world of cosmology, it's huge. It's like two clocks ticking at different speeds, and no one knows why. So why does this matter? Because the Hubble constant isn't just a number. It's a cornerstone of our understanding of the universe's age, size, and ultimate fate. If we can't agree on how fast space is stretching, it calls into question everything from the timing of the Big Bang to the nature of dark energy. The CMB's role here is critical. It acts as a cosmic yardstick, capturing the universe's baby picture and letting us extrapolate its growth over billions of years. But if that yardstick is giving us different answers than the tools we use today, something's missing in our theories. What could explain the tension? Some speculate there's undiscovered physics lurking in the early universe, perhaps a new type of dark energy that tweaked expansion rates in the cosmos's first moments. Others wonder if dark matter behaves differently than we thought, or if there's a flaw in how we interpret CMB data. Then there's the unsettling possibility that both methods are right, and the universe's expansion rate has somehow changed over time, defying our current models. The stakes couldn't be higher. If the Hubble tension holds up, it could mean rewriting textbooks. Imagine discovering that the universe isn't just expanding, but doing so in ways we never predicted. Future missions like the James Webb Space Telescope are diving into this mystery, cross-checking measurements with ever greater precision. But for now, the CMB remains our most powerful tool, and its disagreement with local observations is one of cosmology's most tantalizing unsolved problems. Whether it's hidden physics, measurement errors, or something entirely unexpected, the Hubble tension reminds us that even our best cosmic maps still have blank spots waiting to be filled. Now, let's take a step back in time to uncover a surprising twist in the cosmic microwave background story, one that reminds us how close we came to missing it entirely. It's easy to assume that such a monumental discovery was inevitable, but the truth is, the CMB almost slipped through our fingers. Back in the 1940s and 50s, the idea of detectable relic radiation from the Big Bang was far from mainstream. In fact, many theorists dismissed it outright. The prevailing view was that if the universe began in a hot, dense state, any leftover radiation would have stretched into undetectable wavelengths over billions of years. It seemed like a dead end until a team led by George Gamow, a brilliant but often overlooked physicist, dared to think differently. Gamow and his colleagues, Ralph Alpher and Robert Herman, calculated that if the Big Bang was real, the universe should be filled with a faint glow cooled to just a few degrees above absolute zero. Their work was groundbreaking. They even predicted the CMB's temperature with remarkable accuracy, estimating it would be around 5 Kelvin. But here's the kicker, no one rushed to check. Why not? Part of it was timing. Gamo's team published their prediction in the late 1940s, years before radio astronomy had the tools to detect such subtle signals. But there was also a deeper issue, skepticism. Many scientists, including some of Gamo's peers, were wedded to rival theories like the steady-state model, which rejected the idea of a fiery cosmic beginning. Without the urgency to test Gamo's prediction, the CMB remained hidden in plain sight, a whisper of the Big Bang waiting to be heard. The irony is thick. The very radiation that would later crown the Big Bang theory as the definitive origin story of the universe was initially ignored. Even when Penzias and Wilson stumbled upon the CMB in 1965, they didn't immediately recognize it for what it was. They were radio astronomers troubleshooting antenna noise, not cosmologists hunting for primordial light. It took physicist Robert Dick's team, who were actively searching for the CMB, to connect the dots and realize Penzias and Wilson had found the smoking gun of the Big Bang. Think about that for a second. The discovery that reshaped our understanding of the cosmos was almost lost to history, first because theorists underestimated its detectability, then because the right tools and urgency weren't there. Gamo's team had the math but lacked the means to test it. Penzias and Wilson had the data but needed Dick's insight to grasp its significance. It's a humbling reminder that science doesn't always move in straight lines. Breakthroughs can languish in notebooks or hide in static until someone pieces together the bigger picture. So the next time you hear about the cosmic microwave background, remember, it's not just a relic of the universe's birth. It's also a relic of scientific serendipity, a testament to how even the most brilliant ideas can go unnoticed until the right moment, the right tools, and the right minds collide. And who knows, there might be other cosmic secrets out there, waiting for their own accidental discovery. Now, let's zoom in on one of the most mind-bending aspects of the cosmic microwave background, the tiny ripples that hold the fingerprints of the universe's quantum origins. What if I told you that the vast cosmic web of galaxies, stretching billions of light years across, owes its existence to subatomic jitters smaller than an atom? That's the magic hidden in the CMB's fluctuations. Picture the universe in its infancy, just moments after the Big Bang. At this scale, the rules of quantum mechanics reign supreme, where particles pop in and out of existence in a frenzy of uncertainty. These quantum fluctuations, random, microscopic blips in energy, were baked into the fabric of spacetime itself. Normally, they'd vanish as quickly as they appeared. But in the early universe, something extraordinary happened. During a period called cosmic inflation, the universe expanded faster than light itself, stretching those quantum quirks from subatomic scales to cosmic proportions. Think of it like blowing up a balloon with tiny dots on its surface. As the balloon inflates, the dots grow into vast patterns. By the time the CMB was emitted, 380,000 years after the Big Bang, those stretched quantum fluctuations had imprinted themselves as slight temperature variations, hotter and cooler spots in the primordial glow. We're talking differences of just 1 part in 100,000, but these imperfections were cosmic gold. Gravity began tugging slightly harder on the denser, hotter regions, pulling matter together over billions of years. The result, the seeds for everything we see today, galaxies, clusters, and the sprawling filaments of the cosmic web. Here's where it gets even wilder. The pattern of these fluctuations isn't random noise. It follows a precise mathematical signature predicted by quantum mechanics and inflation. When scientists analyzed data from satellites like Planck, they found the CMB's temperature variations match what you'd expect if quantum randomness was stretched across the sky. It's as if the universe left us a recipe: start with quantum uncertainty, add inflation, and wait 13.8 billion years. But wait, there's a twist. Some of these fluctuations appear a bit too pronounced or oddly aligned, defying standard predictions. Could there be deeper quantum secrets lurking in the CMB? A few theories suggest these anomalies might hint at exotic physics, like higher dimensions or a multiverse. While still speculative, it's a reminder that the CMB isn't just a relic. It's a living puzzle, whispering questions we're only beginning to decode. So the next time you look up at the night sky, remember this: the stars and galaxies above owe their existence to quantum quirks smaller than atoms, frozen in time as faint wrinkles in the cosmic microwave background. It's a staggering thought that the universe's grandest structures grew from the tiniest tremors of randomness. And who knows, the answers to quantum gravity or the nature of reality itself might still be hiding in that ancient light, waiting for the next bold mind to listen. Now, here's something that might surprise you. Despite being the oldest light in the universe, the cosmic microwave background is completely invisible to us without the right tools. That's right, you could stare into the night sky forever and never see it. Why? Because the CMB isn't visible light, it's microwave radiation, a type of energy our eyes simply aren't built to detect. Think of it like tuning into a radio station. Your ears can't hear the music until the radio converts those invisible waves into sound. Similarly, the CMB's whisper from the dawn of time only becomes visible when we use special instruments, like radio telescopes or satellites, to translate those ancient microwaves into something we can study. In fact, the most detailed maps of the CMB come from missions like Planck and the Wilkinson Microwave Anisotropy Probe, which spent years scanning the sky to capture this faint glow with precision. But here's a fun nugget of trivia. You've actually heard the CMB before, or at least a tiny fraction of it. Remember the static snow on old analog TVs? About 1% of that chaotic noise was literally the afterglow of the Big Bang bleeding into your living room. Those crackling pixels were partly the universe's baby photos mixing with terrestrial interference. It's a wild thought. For decades, humanity unknowingly had cosmic fossils flickering in the background of sitcoms and news broadcasts. Now, why microwaves? It all comes down to stretching. When the CMB was first emitted, it was blazing hot around 3000 Kelvin, glowing invisible and infrared light. But over 13.8 billion years, the expansion of the universe stretched that light into much longer, cooler wavelengths, like a cosmic rubber band pulling the light's energy thinner and thinner. Today, those photons have redshifted all the way into the microwave part of the spectrum, with a temperature of just 2.7 Kelvin. This invisibility is actually a gift to science. Because the CMB isn't drowned out by stars or galaxies, it's the cleanest signal we have from the early universe. Imagine trying to hear a single violin in a packed concert hall. That's what studying other cosmic light sources can feel like. But the CMB, it's like that violin playing in an empty room. No distractions, just pure, unfiltered history. And here's the kicker. If our eyes could see microwaves, the entire sky would look like a uniform glow, brighter than all the stars combined. The CMB is everywhere, a blanket of radiation left over from when the universe was a scalding plasma soup. It's humbling to realize we're literally bathed in this ancient light every second, even if we can't perceive it. So next time you look up at the stars, remember there's an even older story written in light you can't see, waiting to be decoded by the ingenuity of radio dishes and space telescopes. And who knows, maybe future generations will develop tech that lets us see the CMB directly, turning the universe's oldest glow into a shared human experience. Until then, we'll keep listening to its whispers through the tools we have, uncovering secrets from a time before time. Here's something truly mind-bending. The cosmic microwave background doesn't just tell us about light from the early universe. Hidden within its subtle patterns is a ghostly whisper from an even earlier time, a shadowy relic known as the cosmic neutrino background. Picture this: while the CMB captures the universe at 380,000 years old, neutrinos, those nearly massless, ultra-shy particles, were already racing through space just 1 second after the Big Bang. And here's the wild part. We've never directly detected this cosmic neutrino background, but the CMB acts like a cosmic detective, revealing its fingerprints. So how does it work? When the universe was a searing, dense soup of particles, neutrinos were born in unimaginable numbers, trillions passing through you every second without a trace. These particles are so light and weakly interacting that they slipped free from the primordial plasma long before atoms even formed. Unlike light, which was trapped until the CMB's release, neutrinos streamed away unimpeded, carrying secrets from the universe's first heartbeat. But because they're so elusive, we can't catch them with current technology. That's where the CMB comes in, those tiny temperature fluctuations in the CMB. They're not just random, they're a cosmic ledger recording how matter clumped together in the early universe, and neutrinos left their mark on that ledger. Here's the key: as they fled the newborn cosmos, their sheer speed and energy subtly pushed against the denser regions of matter, like a breeze nudging smoke. This left a distinct imprint on how galaxies later formed, an imprint we see echoed in the CMB's patterns. By studying these distortions, scientists can infer the presence and properties of the cosmic neutrino background, almost like reading a message in invisible ink. The real jaw-dropper: this neutrino background is older than the CMB itself. It's a fossil from when the universe was a scorching 1 second old, a time so early that protons and neutrons were still forming. And thanks to the CMB's clues, we know it's out there, a universe-spanning sea of these phantom particles, colder than the CMB but just as ancient. Experiments like the Planck satellite have even used the CMB to estimate how many neutrino species exist, confirming with stunning precision that there are exactly 3, matching what particle physics predicts. What's next? While we've yet to build a detector sensitive enough to catch these primordial neutrinos directly, they're now chilled to just 1.95 Kelvin, barely above absolute zero. The CMB keeps giving us indirect glimpses. It's a reminder that sometimes, to uncover the universe's deepest secrets, you don't need to see the hidden player. You just need to read the ripples they left behind. And who knows, maybe one day we'll develop technology to snag these ghostly particles straight from the dawn of time, adding another chapter to the story written in the CMB's light. Until then, we'll keep decoding their subtle echoes, tracing the universe's shadowy beginnings one neutrino at a time. Now let's shift gears to something that's left scientists scratching their heads: a peculiar quirk in the cosmic microwave background known as the axis of evil. If the CMB is supposed to be the ultimate snapshot of a uniform, isotropic universe, meaning it should look the same in all directions, why does it seem to have a preferred direction? This anomaly throws a wrench into one of cosmology's most basic assumptions, and it's got researchers both intrigued and a little unnerved. Here's the mystery: when scientists mapped the CMB's temperature fluctuations, they expected to see randomness like static on an old TV screen. But instead, they noticed something bizarre. Certain patterns in the hot and cold spots weren't scattered randomly. They appeared to align along a specific axis, almost as if the universe had a subtle tilt. Dubbed the axis of evil, yes, that's its real name, and no, it's not as ominous as it sounds. This alignment defies the standard cosmological principle that the universe has no special direction or center. So what's going on? One possibility is that we're seeing a statistical fluke, a cosmic coincidence that stands out because we've only got one universe to observe. But the odds of this happening by chance are slim, around 1 in 1,000. That's like rolling a die and getting the same number 10 times in a row. Unlikely, but possible. Still, scientists don't like leaving things to chance, especially when it challenges bedrock theories. Another idea is that there's some unaccounted for local effect skewing our measurements. Maybe our galaxy's motion, or even dust in the solar system, is imprinting this pattern onto the CMB. Yet even after painstakingly ruling out these foreground contaminants, the anomaly persists. That leaves the door open to wilder explanations. Could it be evidence of a pre-Big Bang structure, a shadow of a neighboring universe, or even a flaw in our understanding of gravity itself? The axis of evil isn't just a curiosity, it's a potential crack in the foundation of modern cosmology. If the universe does have a preferred direction, it could mean our models are missing something profound, like an unseen force or a cosmic asymmetry baked into space-time from the very beginning. Some theorists have even speculated that this axis might trace back to the universe's birth, a relic of quantum irregularities during inflation that never fully smoothed out. For now, the axis of evil remains one of the CMB's most stubborn puzzles. Future missions, like more sensitive CMB telescopes or even gravitational wave detectors, might shed light on whether this is a measurement glitch, a cosmic illusion, or something far weirder. Until then, it's a humbling reminder that the universe, even in its oldest light, still has a few tricks up its sleeve. And that's what makes science so thrilling. Sometimes the anomalies teach us more than the rules ever could. Now let's take a step back and look at the bigger picture, because the cosmic microwave background doesn't just tell us about the universe's past. It also holds eerie clues about its ultimate fate. Imagine the CMB as a cosmic crystal ball, and the readings we've gathered from it point to one unsettling possibility. The universe might end not with a bang, but with a long, silent freeze. Here's how it works. The CMB's detailed maps have helped scientists measure the universe's expansion rate with incredible precision. And what they've found is that dark energy, the mysterious force pushing galaxies apart, isn't just sticking around. It's winning. Over trillions of years, as dark energy accelerates the universe's expansion, galaxies will drift so far apart that their light can't reach us anymore. Stars will burn out, new ones will stop forming, and eventually, even black holes will evaporate. The cosmos will become a vast, dark, near-empty void, barely above absolute zero. Scientists call this the Big Freeze or the heat death scenario, and the CMB's fingerprints are all over the theory. How does the CMB predict this? It's all in the numbers. The temperature fluctuations and polarization patterns in the CMB reveal how much dark energy is out there, and it makes up a staggering 68% of the universe's total energy budget. That's more than twice the amount of dark matter and 13 times the amount of ordinary matter like stars and planets. With numbers that lopsided, dark energy's influence isn't just strong, it's inevitable. But here's the twist. The CMB doesn't just show us that the universe is expanding. It also tells us how that expansion is changing over time. By studying the CMB's subtle distortions, scientists have confirmed that dark energy's push is constant, or might even be getting stronger. That means the universe isn't just growing, it's growing faster, like a runaway train with no brakes, and in a future so distant it's hard to fathom. That acceleration will leave the cosmos cold, dark, and eerily still. Of course, the Big Freeze isn't the only possible ending. Some theories suggest dark energy could evolve in unexpected ways, leading to a dramatic Big Rip, where even atoms are torn apart, or a cyclical rebound where the universe collapses and starts anew. But right now, the CMB's data fits the Big Freeze scenario best. It's a humbling thought. The same ancient light that illuminates the universe's infancy also whispers about its distant demise. So what does this mean for us? Well, on a cosmic timescale, humanity's existence is barely a flicker. But the CMB's message isn't just about doom and gloom. It's a reminder that the universe is dynamic, full of phases and transformations. And while the Big Freeze might be the long-term forecast, there's still so much to discover, and so much time to discover it before the lights go out for good. Now, let's shift our focus to something truly extraordinary: how the cosmic microwave background hasn't just reshaped our understanding of the universe, but also earned some of the highest honors in science. The CMB's discoveries have been so groundbreaking that they've snagged not one, but multiple Nobel Prizes, cementing its place as one of the most revolutionary findings in modern cosmology. It all started in 1978 when Arno, Penzias and Robert Wilson were awarded the Nobel Prize in Physics for their accidental discovery of the CMB back in 1965. Remember those two engineers trying to fix noisy radio antennas? Turns out their cosmic static was the smoking gun for the Big Bang theory, overturning decades of debate about the universe's origins. The Nobel Committee didn't just reward their technical skill, they celebrated a discovery that proved the universe had a beginning, forever changing how we see our cosmic home. But the CMB's Nobel story doesn't end there. Fast forward to 2006 and another duo, John Mather and George Smoot, took home the prize for their work with NASA COBE satellite. COBE did something astonishing. It captured the first precise map of the CMB's tiny temperature fluctuations, those millionth of a degree variations we talked about earlier. These wrinkles in the fabric of space-time revealed the seeds of all cosmic structure, from galaxies to galaxy clusters. Smoot famously called it the handwriting of God, and the Nobel Committee agreed, hailing their work as the cornerstone of precision cosmology. What's remarkable is how these prizes underscore the CMB's dual role in science. Penzias and Wilson found the CMB, but Mather and Smoot decoded it, turning a faint whisper of radiation into a detailed blueprint of the early universe. Together, their discoveries bridged theory and observation, proving that the cosmos could be measured, mapped, and understood like never before, and the ripple effects didn't stop there. The CMB's legacy inspired even more breakthroughs, like the Planck satellite's ultra-high-resolution maps and the BICEP experiments hunting for primordial gravitational waves. While these later missions haven't won Nobels yet, they're built on the foundation laid by those earlier pioneers, proof that the CMB keeps giving us new answers decade after decade. So why does this matter? Because Nobel Prizes aren't just about prestige, they're a spotlight on ideas that redefine what's possible. The CMB didn't just earn gold medals, it transformed cosmology from a speculative field into a hard science where hypotheses could be tested against real data. And that's the real triumph here. The universe's oldest light didn't just illuminate the past, it lit the way for every discovery that followed. Now, let's venture into one of the most mind-bending possibilities tied to the cosmic microwave background. What if hidden within its faint whispers are clues to dimensions beyond our own? Here's the wild idea. String theory, a leading candidate for a theory of everything, suggests our universe might have more than the three spatial dimensions we experience. Some versions of the theory propose up to 10 dimensions, all curled up and hidden from our perception. But how could the CMB, something so ancient and seemingly straightforward, hint at these extra dimensions? It all comes down to anomalies. Remember those tiny temperature fluctuations in the CMB we've talked about? Most of them fit neatly into our standard models, but a few stubborn patches don't. One example is the infamous cold spot, a strangely large, chilly region in the CMB that some scientists speculate could be a cosmic bruise, a mark left by a collision with another universe in the multiverse. Others think it might be a shadow cast by an extra dimension warping the fabric of space-time. Here's how it might work. If extra dimensions exist, they could subtly alter how gravity behaves on cosmic scales, leaving faint imprints in the CMB's patterns. Think of it like a sheet of paper with invisible folds. Light traveling through it would bend in ways we can't fully explain with just 3 dimensions. The CMB, as the most far-reaching light we can observe, might carry those gravitational fingerprints. Experiments like the Planck satellite have scoured the CMB for these oddities, and while some anomalies do stand out, the data isn't conclusive. Critics argue these could just be statistical flukes or artifacts of how we process the CMB's sprawling data. After all, when you're mapping the entire observable universe, a few weird pixels are bound to pop up by chance. But the tantalizing part, if even one of these anomalies were linked to extra dimensions, it would revolutionize physics overnight. Suddenly, string theory's abstract math could have real-world evidence, and our understanding of reality would expand literally into uncharted territory. For now, though, it's a cosmic waiting game. Future CMB experiments with even sharper resolution might settle the debate, either by confirming these anomalies or smoothing them away as measurement noise. So while we can't yet say the CMB holds proof of other dimensions, it's thrilling to think that the universe's oldest light might still be hiding its most extraordinary secrets. And if those secrets include hidden dimensions, well, that would be a Nobel-worthy discovery for a whole new generation of scientists. Up next, we'll explore how the CMB's patterns aren't just cosmic static, they're frozen echoes of sound waves that shape the entire universe. Now, let's turn our attention to something truly extraordinary. The cosmic microwave background isn't just a silent relic of the early universe, it's actually carrying echoes of the cosmos's first sounds. That's right, the CMB holds the faint imprint of primordial sound waves that helped sculpt the universe as we know it. These cosmic vibrations are called baryon acoustic oscillations, and they're essentially the universe's first symphony, frozen in time. Here's how it happened. In the fiery infancy of the cosmos, just a few 100,000 years after the Big Bang, the universe was a searing plasma soup of particles and radiation. Photons and baryons, the particles that would later form atoms, were locked in a violent dance, pushing and pulling against each other. The photons exerted pressure, creating ripples of sound that traveled outward like waves in a pond. But when the universe cooled enough for atoms to form, releasing the CMB we see today, those sound waves suddenly froze in place. Imagine a recording of a song suddenly paused. The vibration stopped midair, leaving behind a permanent snapshot of their structure. These frozen waves then acted as cosmic blueprints, determining where matter would eventually clump together. What's mind-blowing is that we can still see their handiwork. The CMB's temperature variations reveal peaks and troughs corresponding to the loudest and quietest parts of these ancient sound waves. And because these oscillations had a predictable scale, about 500 million light-years across, they left a telltale pattern in the distribution of galaxies. When astronomers map the universe today, they find galaxies tend to cluster at roughly this same distance apart, like beads strung along an invisible cosmic web. This isn't just theoretical. Surveys like the Sloan Digital Sky Survey have confirmed this spiderweb-like arrangement of galaxies matches the scale of baryon acoustic oscillations imprinted in the CMB. It's as if the universe left breadcrumbs for us to follow, a fingerprint of its own creation. But why does this matter? Because these sound waves aren't just a curiosity. They're one of our most precise cosmic measuring tapes. By studying how galaxies align with these oscillations, scientists can track the expansion of the universe with remarkable accuracy, helping us understand dark energy's role in shaping cosmic destiny. And here's the kicker, these oscillations also serve as a test for our theories. If the universe had different amounts of dark matter or dark energy, the spacing of these galaxy clusters would change. The fact that they match predictions so perfectly gives us confidence that our models of the cosmos are on the right track. So next time you look up at the night sky, remember, the galaxies you see aren't scattered randomly. They're arranged by the echoes of sound waves from the dawn of time, a hidden rhythm written into the fabric of space itself. Coming up, we'll explore another startling truth about the CMB. It's slowly fading into silence, a cosmic whisper destined to disappear forever. Here's the script section for Thing 21, seamlessly continuing from the previous segment. Shifting our gaze to the far future, there's a bittersweet truth about the cosmic microwave background. It won't be with us forever. Right now, the CMB is our most direct link to the infant universe. But thanks to the relentless expansion of space, this ancient light is slowly fading into oblivion. Here's why. The CMB started as searing, visible light just after the Big Bang, but over billions of years, the stretching of the cosmos has stretched its wavelengths too, shifting it into the microwave range we detect today. This process called redshift isn't stopping. As the universe continues to expand, the CMB's light will stretch even further, sliding from microwaves into longer and longer radio waves. Eventually, those wavelengths will become so faint and spread out that they'll be virtually undetectable. Imagine tuning an old radio to a distant station, only for the signal to dissolve into static. That's the fate awaiting the CMB. Current estimates suggest that in about 100 trillion years, the CMB's redshift will push its radiation beyond any practical observational limit. The temperature, already a frigid 2.7 Kelvin, will plummet closer to absolute zero, blending into the cosmic void. For any civilizations that arise in that distant era, the afterglow of the Big Bang will be invisible, leaving them with no obvious clue that the universe had an explosive beginning. This raises a fascinating question. How would future astronomers piece together cosmic history without the CMB? Today, it's our Rosetta Stone for decoding the universe's origins, revealing everything from its age to its composition. Without it, scientists would need to rely on far more indirect evidence, like the motions of ancient stars or the faint echoes of galaxy collisions, to reconstruct the past. It's a sobering reminder that we're living in a privileged cosmic era, one where the universe's secrets are still written in light. But here's the twist: while the CMB is vanishing, its legacy is permanent. The structures it helped seed, galaxies, clusters, and the vast cosmic web, will endure far longer, etched into the universe's architecture. Even when the last whisper of the CMB fades, its fingerprints will remain, hidden in the arrangement of matter it left behind. So while we can, let's keep listening to this cosmic lullaby, a fading echo of creation that for now still has stories to tell. Transition subtly into the next section without repeating phrasing, e.g. Now, let's uncover another surprise. The entire map of the CMB fits into something you might find in your living room. Here's the next section, seamlessly continuing the narrative with a fresh perspective and unique transition. Now, here's something that might just blow your mind. The cosmic microwave background, this colossal fingerprint of the entire observable universe, can be squeezed onto a single DVD. Yes, you heard that right. The Planck satellite's monumental map of the CMB, a dataset so rich it reveals the universe's structure down to tiny temperature fluctuations, compresses into something you could hold in your hand. It's like fitting the blueprint of a skyscraper onto a postage stamp. Let's unpack how this is possible. The Planck mission, launched in 2009, spent over 4 years scanning the sky with unparalleled precision, capturing the CMB's subtle variations in excruciating detail. But raw data from such a mission would be enormous, think terabytes upon terabytes. However, scientists use clever compression techniques to distill the essence of the CMB into manageable forms. By focusing on the most meaningful patterns, those temperature differences as tiny as 1 part in 100,000, they strip away redundant noise, preserving only the universe's signal. The result? A dataset about 4.7 gigabytes in size, snugly fitting on a standard DVD. This compression isn't just about convenience. It reflects a deeper truth about the CMB itself. For all its cosmic grandeur, its information is remarkably orderly. Those fluctuations we've talked about, they follow predictable mathematical relationships like harmonies in a symphony. That's why compressing the data works so well. The universe at its birth was singing a tune with repeating motifs, not random noise. But don't mistake small size for small significance. That DVD's worth of data is a treasure trove. It holds clues to dark matter's pull, dark energy's push, and even the universe's curvature. It's like a cosmic zip file, unpacking into revelations about everything from the Big Bang's physics to the fate of galaxies. And here's the kicker: future missions could refine this data further, but Planck's DVD-sized snapshot might remain the gold standard for decades. So next time you see a DVD, remember, somewhere out there, a scientist might be holding one that contains the echoes of creation itself, and that's a humbling thought. Subtle transition hinting at the next discovery, e.g., speaking of cosmic snapshots, the CMB also holds a precise timestamp for the universe's age. Let's explore that next. Here's your next section, crafted for seamless continuity and fresh engagement. Now, let's turn the cosmic clock back, way back, to uncover one of the CMB's greatest gifts, the universe's birth certificate. Thanks to those faint microwave whispers we've been exploring, scientists have pinned down the age of our cosmos with staggering accuracy, 13.8 billion years. Think about that for a second. We're not dealing with rough estimates or educated guesses here. The CMB delivers a timestamp so precise, it settled century-old debates about whether the universe was eternal or had a fiery beginning. How does light from the Big Bang's afterglow reveal time itself? It all comes down to the CMB's temperature and patterns. When the universe was young, it was a searing plasma, too hot for light to travel freely. But as it expanded and cooled, around 380,000 years after the Big Bang, atoms formed and light finally broke free, creating the CMB we detect today. By measuring how much that light has cooled and stretched, a process called redshift, and by analyzing the size and distribution of its fluctuations, cosmologists can calculate how long the universe has been expanding. It's like finding a fossilized ripple in a pond and working backward to determine exactly when the stone was thrown. The magic number, 13.8 billion, isn't just a headline. It's a triumph of cross-checking. Independent methods like tracking the lives of ancient stars or observing distant supernova all converge on the same answer. But the CMB offers something unique, a snapshot of the universe at its simplest before galaxies cluttered the scene. Freed from later cosmic complications, the CMB's pristine data acts as a clean slate for calculations. What's truly mind-bending is how this number reshaped our cosmic story. Before the CMB, some scientists clung to the steady-state theory, arguing the universe had no beginning. Others guessed its age might be as low as 10 billion years, clashing with older stars seemingly too ancient to fit. The CMB didn't just break the tie, it rewrote the rules. Those tiny temperature variations, they encode the universe's expansion rate, matter density, and even the pull of dark energy. Plug those into Einstein's equations and voila, a definitive age emerges. And here's the kicker, that number keeps getting more precise. Early estimates from the 1990s had error bars of billions of years. Today, thanks to missions like Planck, we're down to a razor-thin uncertainty of just 40 million years. That's like measuring your own age to within a minute. It's a testament to how the CMB, this ancient light, keeps sharpening our view of cosmic history. So next time you gaze at the night sky, remember, every star, every galaxy, even the emptiness between them, shares that same 13.8 billion-year-old birthday. And thanks to the CMB, we're not just guessing, we're reading the universe's own diary. Subtle pivot to the next discovery. But the CMB's revelations don't stop there. What if I told you it might also carry messages from advanced civilizations? Let's dive into that wild possibility next. Now, let's take a playful detour into the realm of cosmic science fiction, because what if the CMB isn't just a relic of the past, but a canvas for the future? Imagine an alien civilization so advanced they could tweak the fabric of the universe itself, leaving messages in the cosmic microwave background. Sounds like something straight out of a blockbuster movie, right? But believe it or not, some scientists have seriously floated this wild idea as a thought experiment. Here's how it might work. The CMB's patterns are like a fingerprint, unique and imprinted across the entire sky. If a civilization had technology far beyond ours, they could theoretically manipulate those patterns, say, by creating localized temperature anomalies or polarization signals. Think of it as graffiti on the universe's oldest wall, a way to broadcast their existence to anyone who knows how to look. And because the CMB is observable from every corner of the cosmos, it'd be the ultimate billboard, visible to every budding civilization out there. But before you start scanning the CMB for alien Morse code, let's pump the brakes. This idea is firmly in the realm of speculation, with no evidence to back it up. For one, the energy required to alter something as vast and diffuse as the CMB would be mind-boggling. We're talking about harnessing power on a galactic scale. Plus, any artificial tweaks would have to compete with the natural fluctuations born from quantum randomness in the early universe. Spotting an artificial signal in that cosmic noise would be like finding a single edited pixel in a billion ultra-high-definition photos. That said, the concept isn't totally dismissed. Some researchers argue that if a civilization existed billions of years ago, when the universe was smaller and denser, they might have had an easier time leaving a mark. Others suggest that certain oddities in the CMB, like the infamous cold spot, could, in theory, be examined for signs of tampering, though natural explanations are far more likely. It's a fun puzzle, blending cosmology with the search for extraterrestrial intelligence in ways that stretch our imagination. What makes this idea so tantalizing isn't just the sci-fi thrill, it's what it says about our own curiosity. Humanity has always looked to the stars for meaning, from ancient myths to modern radio telescopes. The idea that we might one day find a message in the CMB speaks to our longing for connection in a vast, seemingly silent universe. Of course, for now, the CMB remains a pristine record of nature's handiwork, not an alien postcard. But the fact that we can even entertain such possibilities shows just how far our understanding of the cosmos has come. So, while we're not holding our breath for ET's cosmic graffiti, the mere thought invites us to ponder. If we ever reach that level of technological mastery, what would we write in the sky for others to find? A hello, a warning, or perhaps just a humble "we were here." The CMB might not hold those answers today, but it sure makes for a stellar daydream. And speaking of cosmic mysteries, our final revelation takes us even deeper into the past because, as it turns out, the CMB isn't the oldest light in the universe after all. Buckle up for one last mind-bender. Now, here's a cosmic plot twist that might just rearrange your understanding of the universe's timeline. While the cosmic microwave background has long held the title of the oldest light we can observe, it turns out there are even more ancient relics lurking in the cosmos, ones that take us back further than photons ever could. Let's peel back the layers of time to uncover what truly lies beyond the CMB. First up, meet the cosmic neutrino background. If the CMB is a snapshot from 380,000 years after the Big Bang, neutrinos offer us a glimpse of the universe a mere 1 second into its existence. These ghostly particles, barely interacting with matter, were unleashed when the cosmos was a seething soup of energy so dense that light couldn't even travel freely. Unlike the CMB, which is a burst of liberated photons, the neutrino background is a faint whisper from an era when the universe was unimaginably hotter and more chaotic. Detecting it is like trying to hear a pin drop in a hurricane, but if we ever do, it would be the ultimate time machine, revealing secrets from the universe's very first breath. Then there's the granddaddy of them all, primordial gravitational waves. These ripples in spacetime itself were born during the inflationary epoch, a fraction of a second after the Big Bang, when the universe expanded faster than the speed of light. While the CMB shows us the aftermath of inflation, gravitational waves could carry direct evidence of the event that set everything in motion. Imagine them as echoes of the universe's first shout, vibrations etched into the fabric of reality. Projects like the Laser Interferometer Space Antenna, or LISA, aim to catch these waves, offering a window into a time before even neutrinos could form. So why hasn't the cosmic neutrino background or gravitational waves stolen the CMB's spotlight? Here's the catch: while they're older, they're also infinitely harder to detect. The CMB is like a high-definition photo, clear, detailed, and packed with information. Neutrinos, on the other hand, are elusive shadows, and gravitational waves are like trying to photograph a whisper. The CMB remains our sharpest tool because its light is abundant and relatively easy to study, giving us a crisp blueprint of the early universe, these other relics. They're the holy grails of cosmology, waiting for technology to catch up to their secrets. But here's what makes this twist so thrilling. The CMB isn't just a relic, it's a Rosetta Stone. Its patterns hint at the presence of these older phenomena, like neutrino densities and inflationary energy, allowing us to infer their existence even before we can observe them directly. It's a cosmic detective story where each clue leads us deeper into the past, and when we finally unlock those older signals, they won't replace the CMB, they'll complete it, painting a fuller picture of how everything began. So while the CMB might have to share its oldest light crown, it's still the cornerstone of modern cosmology. It's the bridge between what we can see and what we've yet to discover, a testament to how much remains hidden in the universe's first moments. And who knows, maybe one day we'll find that the real story begins even earlier, in a time before time, waiting for us to decode its mysteries. Until then, the CMB remains our most dazzling portal into the dawn of everything. As we wrap up this cosmic journey, let's take a final look at the extraordinary legacy of the cosmic microwave background. It's not just a remnant of the Big Bang. It's a time machine carrying whispers from the universe's infancy, a cosmic blueprint that maps out the structure of everything we see today, and a puzzle box brimming with unanswered questions. From confirming the Big Bang to revealing the universe's hidden ingredients like dark matter and dark energy, the CMB has reshaped our understanding of reality itself. Yet, as we've seen, it's also a springboard to even deeper mysteries like the cosmic neutrino background and primordial gravitational waves waiting just beyond our current reach. Now, here's something to ponder. What if the next breakthrough in CMB research uncovers something we haven't even imagined? Could those tiny temperature fluctuations hide clues about parallel universes, or might future telescopes detect patterns that rewrite the story of cosmic inflation? The beauty of science is that every answer leads to new questions, and the CMB is no exception. Before you go, I'd love to hear from you. Which of these 25 facts about the cosmic microwave background blew your mind the most? Was it the accidental discovery by Penzias and Wilson, the eerie axis of evil anomaly, or the mind-bending possibility that the CMB might one day fade into undetectable silence? Drop your thoughts in the comments below. I read every single one, and if you're hungry for more deep dives into the universe's greatest mysteries, don't forget to hit that subscribe button and ring the notification bell so you never miss an update. The cosmic microwave background is more than just ancient light. It's a reminder that the universe is still full of secrets, waiting for curious minds to uncover them. Thanks for joining me on this adventure through space and time. Until next time, keep looking up.